Ice crystals form on Viktor Petrov's breath as he stares at the twisted remains of what was once a perfectly engineered propeller blade, now reduced to jagged metal sculpture by forces that no textbook ever warned him about. The Siberian wind cuts through his wool coat like frozen knives, carrying the sound of 60 Ilyushin Il-4 bombers sitting silent on the runway. Their engines cold, their missions cancelled, their crews watching the sky darken with the approach of a blizzard that will trap them here for days, while German forces consolidate positions that these aircraft were supposed to disrupt. The propeller failure is not mechanical. It's not metal fatigue or design flaw or manufacturing defect. It's something worse, something that challenges everything Viktor learned during his engineering studies at Moscow Aviation Institute. Something that suggests the fundamental assumptions about aircraft operation in extreme conditions might be catastrophically wrong. The blade didn't break cleanly along stress lines that engineers could predict and prevent. Instead, it shattered in a crystalline pattern that speaks of molecular-level destruction, of metal transformed into something brittle and unreliable by temperatures that aviation designers never imagined their aircraft would encounter in operational conditions. But Viktor sees possibility where others see disaster. Not immediate solution, but the beginning of understanding that might lead to breakthrough. The shattered propeller tells a story about material science under extreme stress, about the behavior of aircraft components when pushed beyond their design parameters by conditions that exist at the intersection of human ambition and natural hostility. If he can decode that story, if he can understand what the metal is trying to tell him about its failure, he might discover principles that could save not just these 60 bombers, but every aircraft that will face similar conditions in the war's remaining years. He pulls out his field notebook and begins sketching the fracture patterns, documenting destruction that might contain the seeds of its own solution, mapping failure that could become the foundation for innovation that exists nowhere in any engineering manual, because no engineer has ever been desperate enough to think beyond the boundaries of established metallurgical science. This is February 1943. The Eastern Front stretches across 1,000 miles of territory, where the Wehrmacht and the Red Army have been teaching each other lessons about industrial warfare that no military academy ever included in its curriculum, where tanks and aircraft and artillery operate in conditions that their designers never anticipated because those designers worked in laboratories and factories rather than landscapes, where winter becomes a third combatant more ruthless than any human enemy. The Soviet Union's strategic bombing campaign against German supply lines depends on aircraft that can function reliably in temperatures that turn lubricants solid, make rubber brittle, transform metal components into unpredictable variables in equations that must be solved correctly, or pilots die. The Il-4 bombers grounded at this Siberian airfield represent months of industrial production, thousands of man-hours of assembly work, the concentrated technical knowledge of engineers and workers who understand that every aircraft that fails to complete its mission allows German forces additional time to consolidate defensive positions, to strengthen supply lines, to prepare for spring offensives that could determine whether the Soviet Union survives as an independent nation or becomes another conquered territory in the expanding German Empire. But industrial production means nothing if the aircraft cannot function under operational conditions. The propeller failures that have grounded 60 bombers are not isolated incidents, but symptoms of systematic problems that threaten the entire Soviet bombing campaign. The metal alloys that perform perfectly in moderate climates become unreliable when exposed to Arctic conditions that exist at the intersection of altitude and latitude, where atmospheric pressure and temperature create stresses that laboratory testing never replicated, because laboratory testing assumes controlled conditions rather than the chaotic variables that characterize actual warfare. Viktor understands that solving the propeller problem requires thinking beyond conventional metallurgy, beyond the established principles that govern aircraft design under normal circumstances. The failures he observes suggest that extreme cold is not simply making metal more brittle, but actually changing its molecular structure in ways that create new failure modes, new patterns of destruction that require new approaches to material science and engineering design. It's not enough to strengthen existing alloys or modify manufacturing processes. The solution requires fundamental rethinking of how metal behaves when subjected to stresses that exist outside the range of normal engineering experience. The breakthrough begins with careful examination of the failure patterns under magnification that reveals crystalline structures unlike anything Viktor has seen in conventional metallurgical analysis. The metal has not simply broken. It has been transformed at the molecular level by the interaction of extreme temperature, mechanical stress, and vibration frequencies that create resonance effects never anticipated by Propeller. Designers who worked under the assumption that their products would operate within reasonable environmental parameters rather than at the absolute limits of material tolerance. The crystalline patterns suggest that the metal is attempting to reorganize itself under stress, seeking new molecular arrangements that might provide stability under conditions that its original structure cannot accommodate. Instead of viewing this transformation as failure, Viktor begins to consider it as information, as evidence of the metal's capacity for adaptation that might be directed rather than simply endured, controlled rather than prevented, utilized rather than overcome through brute engineering force. The revolutionary idea emerges gradually, through the kind of systematic observation that good engineers employ when confronting problems that exist outside established knowledge. What if the metal's tendency to reorganize under extreme stress could be encouraged rather than resisted? What if propeller blades could be designed to take advantage of molecular transformation rather than being damaged by it? What if the crystalline patterns that seem to indicate failure actually represent the metal's attempt to achieve greater stability under impossible conditions? Viktor begins experimenting with heat treatment processes that deliberately introduce controlled molecular reorganization before the propellers are exposed to operational stress, essentially pre-adapting the metal to conditions that would otherwise cause catastrophic failure. It's metallurgical heresy, violating principles that every materials science textbook presents as fundamental laws governing the relationship between molecular structure and mechanical properties. But heresy becomes innovation when conventional wisdom proves inadequate to survival requirements that exceed the parameters within which conventional wisdom was developed. The first experimental propeller undergoes heat treatment that would be considered destructive under normal circumstances, subjected to temperature cycles that deliberately stress the molecular structure beyond established safety margins, forced to reorganize its crystalline patterns under controlled conditions rather than waiting for operational stress to cause uncontrolled transformation. The process takes 18 hours of precise temperature management, careful monitoring of metallurgical changes that occur gradually, systematically, in ways that allow the metal to adapt rather than simply endure. When the treated propeller is tested under simulated Arctic conditions, it performs differently than conventional metallurgy predicts. The blade demonstrates greater flexibility without loss of strength, maintains structural integrity under temperature variations that destroy untreated metal, shows resistance to the resonance effects that cause catastrophic failure in conventional propellers operating under extreme stress. The molecular reorganization that seemed like evidence of material failure proves to be the foundation for superior performance under impossible conditions. But laboratory success under controlled conditions is different from battlefield reliability under combat stress. The treated propeller must function not only in extreme cold, but under the additional stresses of combat maneuvering, anti-aircraft fire, mechanical vibrations that occur when aircraft operate at maximum performance levels while carrying full bomb loads over enemy territory. Viktor understands that his innovation must prove itself under conditions that combine environmental extremes with operational demands that push both aircraft and crews to their absolute limits. The installation process requires modifications to standard propeller mounting procedures, adjustments to engine timing that account for the different mechanical properties of the treated metal, calibration of control systems that must accommodate propellers that respond differently to pilot input than their conventional predecessors. Each bomber that receives the experimental propellers becomes a test platform for innovations that exist nowhere in official maintenance manuals. Modifications that violate established protocols because established protocols proved inadequate when tested against the reality of Arctic warfare. The first operational test occurs during a bombing mission against German supply depots located deep in occupied territory, a flight that requires sustained operation at maximum altitude in temperatures that have already grounded conventional aircraft. The experimental propellers perform flawlessly throughout the 8-hour mission, maintaining structural integrity under combat stress, demonstrating that Viktor's molecular reorganization process creates reliability rather than simply preventing failure. The bombers complete their mission and return to base with mechanical systems that function normally despite operating conditions that would have destroyed conventional equipment. Word of the propeller breakthrough spreads through Soviet aviation engineering networks with the speed that important innovations achieve when they address critical problems that threaten operational capability. Aircraft manufacturers begin incorporating Viktor's heat treatment process into standard production procedures, modifying assembly lines to accommodate the additional time and precision required for molecular reorganization that must be carefully controlled to achieve beneficial results rather than random metallurgical damage. The engineering teams responsible for maintaining combat aircraft in the field receive training in the new propeller technology, learning to recognize the different performance characteristics of treated metal, understanding how to maintain and repair propellers that behave differently from conventional equipment. The knowledge spreads through informal networks of mechanics and engineers who understand that survival often depends on technical innovations that exist outside official manuals, modifications that work reliably even when they violate established principles. But the most significant impact occurs at the strategic level, where Viktor's innovation transforms the Soviet Union's capacity to maintain air operations during winter months that previously forced suspension of bombing campaigns. Aircraft that can function reliably in Arctic conditions extend the operational season, maintain pressure on German supply lines during periods when the Wehrmacht expected respite from air attack, demonstrate that technological innovation can overcome environmental limitations that seemed absolute. The 60 bombers that were grounded by propeller failures become the test fleet for Viktor's revolutionary metallurgy, each aircraft receiving experimental propellers that transform catastrophic failure into operational advantage. The bombers resume their missions against German targets, flying in conditions that ground enemy aircraft, operating with reliability that allows mission planning based on strategic objectives rather than weather constraints that previously determined when and where Soviet air power could be employed effectively. The blizzard that threatened to trap the bombers for days becomes cover for operations that German forces never anticipated. Concealment for bombing runs that achieve complete tactical surprise because the Wehrmacht's defensive planning assumed that weather conditions would prevent Soviet air operations. The aircraft that should have been grounded by metallurgical failure instead achieve mission success that demonstrates the strategic value of engineering innovation under impossible circumstances. Viktor's field notebooks become classified documents that influence aircraft design philosophy throughout the remaining war years and beyond. The principles he discovered under survival pressure. That material failure often indicates the need for different approaches rather than stronger materials, that extreme conditions can be accommodated through adaptation rather than simply resisted through engineering force. These insights prove applicable far beyond propeller design to include engine components, structural elements, electronic systems that must function reliably under stresses that exceed normal design parameters. The heat treatment process that began as desperate improvisation becomes standard procedure for aircraft operating in extreme environments. incorporated into manufacturing specifications that assume rather than avoid the kind of challenging conditions that revealed the limitations of conventional metallurgy. Engineering schools begin teaching courses in extreme environment materials science, preparing new generations of engineers to think beyond the comfortable assumptions that govern design under normal circumstances. Years after the war ends, when aviation engineers design aircraft for polar exploration, high-altitude research, space operations that involve temperature extremes beyond anything encountered during terrestrial flight, they study Viktor's wartime innovations in molecular reorganization under stress. The principles he discovered while trying to save 60 bombers from Propeller failure become foundation knowledge for engineering that must function reliably in environments where conventional materials. Science provides inadequate guidance for design decisions. The metallurgical breakthrough that saved the bombing mission proves applicable to industries far removed from aviation, wherever materials must function under extreme conditions that reveal the limitations of conventional engineering approaches. Steel production, chemical processing, nuclear reactor components, automotive applications that involve temperature extremes or mechanical stresses beyond normal parameters all benefit from understanding that materials can be adapted to extreme conditions rather than simply strengthened to resist them. But perhaps the most important legacy lies in the demonstration that impossible problems often require thinking beyond the boundaries of established knowledge, that innovation emerges from the willingness to question fundamental assumptions when those assumptions prove inadequate to survival requirements. Viktor's refusal to accept that propeller failure was inevitable under Arctic conditions led to discoveries that changed how engineers approach material science under extreme stress, how designers think about the relationship between environmental challenges and technological solutions. The Siberian airfield where Viktor achieved his breakthrough remains operational, now serving civilian aviation that benefits from cold-weather technologies developed under wartime pressure. Modern aircraft that fly polar routes, that operate in conditions that would have grounded earlier generations of equipment, depend on materials, science principles that began with one engineer's determination to find solutions, where textbooks insisted only problems existed. Innovation where conventional wisdom saw only limitation. Sometimes the greatest breakthroughs occur when engineers refuse to accept the limitations that established knowledge presents as immutable facts, when desperate circumstances force consideration of approaches that comfortable conditions never require. Viktor saw possibility where metallurgy manuals saw impossibility, recognized opportunity where conventional engineering saw only disaster, understood that survival sometimes requires techniques that violate established principles in service of results that established principles cannot achieve. The propeller blades that shattered in crystalline patterns were trying to tell him something about the metal's capacity for adaptation under impossible stress. When he learned to listen to what the failure was teaching rather than simply trying to prevent it from occurring, he discovered that materials possess capabilities that normal conditions never reveal, that extreme stress can force evolution rather than simply causing destruction. The broken metal became teacher rather than victim, guide rather than casualty, foundation for innovation rather than evidence of limitation. The 60 bombers that should have remained, grounded by impossible metallurgical failure instead, achieved mission success that demonstrated how technical innovation under desperate circumstances can overcome limitations that seemed absolute, transform catastrophic problems into operational advantages, prove that human ingenuity finds ways to succeed when conventional solutions prove inadequate to survival requirements. If stories like this remind you that breakthrough innovation often begins with refusing to accept expert opinion about what is impossible, that materials science contains possibilities that normal conditions never reveal, then perhaps there are other moments when desperate circumstances forced discoveries that changed how we understand the relationship between human problem-solving and the physical laws that seem to limit what engineering can accomplish under extreme conditions.